Where does everything come from? Not the things you can purchase, but everything that exists. Wood, air, iron, the light entering your eyes, the warmth you feel in your hands, even the material that makes a hand possible in the first place. And when we ask, come from, what exactly are we asking? Are we asking what something was made of earlier? Or are we asking why anything exists at all? Those are not the same question, even though we often move between them without realizing it. In physics, that kind of vagueness leads to the biggest misunderstandings, so it helps to separate them carefully. Start with something familiar, a glass of water. You might say water comes from the tap from a reservoir, the reservoir from rainfall, and the rain from clouds. That sounds like a neat chain of sources. But if you keep asking what water actually is, the answer stops being about location and becomes about composition. Water consists of molecules, and each molecule consists of atoms, 2 hydrogen atoms bonded to 1 oxygen atom in a particular arrangement. If you break water down, you won't find wetness hidden inside the pieces. Wetness appears only when countless molecules interact, sliding, colliding, and moving collectively against your skin. So we learn an early lesson. Many properties that feel fundamental don't exist in the individual parts. They emerge from patterns of interaction. If everything comes from something, then origins involve patterns as much as components. So take the next step. Where do atoms come from? For a long time, atoms were imagined as tiny solid spheres, indivisible little beads that had always existed. But later, discoveries showed structure inside them. A dense nucleus sits at the center, with lightweight electrons spread around it. And even the nucleus isn't elementary. It's made of protons and neutrons, which themselves have internal structure. Now the origin question splits again. Are we asking where the raw material came from or where the structure came from? Because even if you had unlimited protons, you wouldn't automatically get oxygen. You would still need the correct numbers combined in the right configuration, bound by the proper forces. So the question shifts. What processes build different atomic nuclei? At this stage, historical discoveries help not as dates to memorize, but as a chain of reasoning. Scientists learned how to identify the composition of matter by studying light. In laboratories, when you heat a gas, it begins to glow. If you pass that light through a prism, it separates into sharp, spectral lines, precise colors at exact positions. Each element produces its own distinct pattern, almost like a fingerprint. The surprising part came when the same spectral signatures were observed in starlight. That meant the stars contain the same types of atoms we find on Earth. This realization was profound. It showed the universe isn't made of isolated, unrelated substances. It operates under the same physical rules everywhere. So, if you want to understand where atoms come from, stars become observable factories. But how does a star actually produce atoms? Imagine a vast cloud of gas, mostly hydrogen, collapsing under its own gravity. As the gas falls inward, particles accelerate and collide more violently. Those chaotic motions generate heat because temperature is simply the measure of microscopic motion. If the temperature climbs high enough, protons begin colliding with such force that their electrical repulsion can be overcome, allowing the nuclear force to bind them together. That process is nuclear fusion. A star isn't burning, in the chemical sense. It's converting mass into energy through nuclear binding changes. This introduces an important principle. Energy is conserved, but it can appear in different accounting forms, and mass is one of them. Starlight, then, comes from tiny amounts of mass being converted into energy during fusion reactions, not destroyed, but transformed with exact proportionality. Now, stars can fuse hydrogen into helium, and helium into heavier elements like carbon and oxygen. You might assume all elements originate in stars, but that's only partly true. Fusion inside ordinary stars can build elements up to iron. Beyond iron, fusion no longer releases energy, it requires energy. So, producing heavier elements like gold or uranium demands far more violent environments: supernova explosions, neutron-star collisions, and neutron-rich events. These extreme processes forge heavy nuclei and scatter them into space. Later, generations of stars and planets form from that enriched material. So the iron in your blood and the calcium in your bones trace back not just to stars, but to stars that lived and died long before the sun formed. But that shouldn't be reduced to a slogan. The key point is that the matter in your body has a traceable physical history, one we can test and reconstruct through observation. Up to this point, the chain looks like this. Molecules form from atoms. Atoms consist of nuclei and electrons. Many nuclei are forged inside stars or during stellar explosions. But then a sharper question appears. What about hydrogen itself? Most ordinary matter in the universe is still hydrogen. If stars build heavier elements out of hydrogen, they can't also be the primary source of hydrogen, because that would require the process running in reverse. So where did hydrogen originate? Following that trail pushes you beyond local factories like stars and toward the overall initial state of the universe. Here, it helps to notice how physics usually answers origin questions. We rarely say something exists because it wanted to or because it's natural. Instead, we describe laws which, given an initial condition, determine what happens next. So when we say everything comes from, we're really talking about two parts: an initial state and laws that evolve that state forward. If you keep tracing origins backward, you eventually run into the initial condition problem. You can always ask what came before the previous state. At some point, you either accept a starting condition or propose a deeper framework that makes it likely. The universe doesn't hand you a receipt explaining the purchase. Now consider what observations tell us about the early universe. This isn't speculation, it's evidence. Galaxies are moving away from one another in a pattern consistent with expansion. If you mathematically reverse that expansion, the universe becomes denser and hotter in the past. There's also a relic of that hot phase, a faint background of microwave radiation filling all space. Its spectrum matches what you'd expect from a once hot thermal environment that cooled as the universe expanded. This radiation isn't theoretical, it's measured directly. It's one of the clearest indicators that the universe was once far hotter and more compact than it is today. In that early high-temperature state, nuclear reactions could occur everywhere, not just inside stars. The young universe functioned like a brief, all-encompassing nuclear reactor, while it expanded and cooled. When physicists calculate what elements would form in that short window, they get mostly hydrogen a substantial amount of helium, small traces of deuterium and helium-3, and a little lithium. And here's the key point. Those predicted ratios match what we observe in ancient gas clouds and pristine cosmic regions. So, hydrogen and most helium weren't made inside stars. They were formed in the early universe itself. Stars came later as refiners, not original producers. At this stage, many people summarize the story by saying everything comes from the Big Bang, but that phrase can conceal as much as it explains. The Big Bang isn't a machine somewhere producing matter. It's a description. The universe was once extremely hot, dense, and expanding. It explains how the universe evolved from an early condition, but it doesn't automatically answer why that condition existed, or what, if anything, came before it. If we're being precise, we have to separate what we know from what we don't. Using well-tested physics, we can describe the universe back to a fraction of a second after its earliest measurable state. Earlier than that, our theories become uncertain because we would need a complete theory of quantum gravity, something not yet experimentally confirmed. So intellectual honesty draws a boundary. We understand much of the story after the universe became extremely young, but not the ultimate origin. Even within that boundary, the origin question sharpens further. At very high temperatures, atoms cannot exist. Electrons and nuclei can't remain bound. Increase the heat further, and even nuclei dissolve into a plasma of protons, neutrons, and other particles. Hotter still, and those particles are better described as excitations of underlying fields. This is one of modern physics' more unsettling lessons. Particles are not always tiny solid objects. They behave more like quantized ripples in fields that fill space. An electron is one type of excitation, a photon is another. So the fundamental stuff of the universe may not be objects at all, but fields and the ways they can vibrate, which leads to a deeper version of the question: where do the fields come from, and why do they have the properties they do? But before jumping there, it helps to notice something else. Not everything originates the way manufactured goods do. Some things aren't produced, they constrain what's possible. Take electric charge. It appears to be conserved. If you start with zero total charge, you always end with zero. You can separate positive and negative charges, but you don't create net charge from nothing. The same applies to energy and momentum under the right conditions. These conservation laws aren't arbitrary, they're tied to symmetries, deep regularities in how physical laws behave across time and space. So part of where things come from is shaped not by sources, but by restrictions, by what the rules forbid as much as by what they allow. Now try a different everyday thought experiment. Imagine completely empty space, no air, no stars, no atoms, just emptiness. In classical physics, you could picture that as truly nothing, perfectly still and featureless. But quantum physics changes that picture. Even in a vacuum, the underlying fields still exist, and they fluctuate. This isn't because of measurement limits or ignorance. It follows from the uncertainty principle and the structure of quantum states. You can't set all field values and their rates of change to exactly zero everywhere. The lowest energy state still carries restless activity. That doesn't mean you can extract unlimited matter from empty space. It means that empty has more structure than everyday language suggests. So when someone asks whether the universe could come from nothing, the first question should be, what definition of nothing? A total absence of laws and fields? Or a quantum vacuum governed by physical rules? Those starting points are radically different. This brings us to the edge of what we can currently describe with confidence. We've traced the material history: heavy elements forged in stars, lighter elements formed in the early universe, and that early universe inferred from expansion and background radiation. We've also seen that matter may be excitations of fields, and that conservation laws and symmetries tightly restrict what can happen. But one question still remains in the background. Where did the laws themselves come from? And why these laws rather than others? Physics can calculate outcomes once equations are assumed, but explaining why those equations exist at all is a deeper challenge. At this point, there are two paths you can take. You can treat the laws as brute facts and focus on their consequences, which alone provides more than enough work for generations of research. Or you can push further and ask whether the laws arise from deeper principles, some selection rule, inevitability, or underlying structure that makes them difficult to be otherwise. But there's a danger here. It's easy to create sentences that sound explanatory without producing testable predictions. In physics, an idea earns its place only if it restricts possibilities and leads to observations you can check. So far, we've moved step by step from a glass of water to atoms, to stars, and then to the early hot universe itself, and each step followed the same rule. Don't stop at labels. Ask what something is made of and what process produces it. But the next step becomes far more slippery, because now the question isn't only about the origin of matter, it's about the origin of the framework that allows matter to exist and evolve at all. If the elements in your body were forged through known stellar processes, if hydrogen formed in an early hot cosmos, and if even empty space isn't truly empty in quantum theory, then what exactly do we mean by the beginning? And what would it even mean for the universe along with its laws to come from anything? Suppose we stay grounded and say the best tested account we have begins with a hot, dense, expanding universe, a model that successfully explains a vast amount of observational data. The next question almost asks itself, what established that initial condition? But notice something subtle. The phrase initial condition already assumes time, a clock, a before and after, and laws capable of evolving states forward. If time itself is part of the universe, then asking what happened before time is like asking what lies north of the North Pole. The words form a sentence, but it's unclear whether they refer to anything physically meaningful. So it helps to separate two puzzles that often get blended together. One puzzle asks why the early universe was hot, smooth, and expanding. That's a scientific question about initial conditions. The other asks why there is a universe and laws at all. That question runs deeper, but it's also more dangerous because it invites answers that may not be testable. Physics advances by turning vague why questions into sharp, measurable ones. Take the smoothness problem as an example. When we observe the universe, especially through the cosmic microwave background, its temperature appears almost uniform in every direction. But if you run cosmic expansion backward using simple models, distant regions of space were never close enough early on to exchange heat or light. So how did they end up at nearly the same temperature? That's not philosophy, it's a quantitative puzzle. One proposed solution is cosmic inflation, a brief period of extremely rapid expansion early in the universe's history. In that picture, a small, causally connected region stretches enormously, explaining the uniformity we observe. The strength of the idea isn't that it sounds grand, it's that it produces testable predictions about temperature fluctuations and matter distribution. Some versions match observations well, others don't. That process of testing trims speculation down to what survives evidence. Even if inflation or something similar did occur, the natural follow-up question appears immediately. Where did that inflationary state come from? And that's exactly the right instinct, because any mechanism you propose simply becomes another link in the chain of origins. Still, each link can be valuable if it connects observable facts. You can think of the early universe like a crime scene with limited evidence, a few remaining clues such as light element abundances, the microwave background radiation, and the large-scale distribution of galaxies. The task is to construct a consistent account that explains those clues without introducing unnecessary assumptions. Now turn to the laws themselves. Are physical laws simply fixed rules written into reality? Or could the laws we observe be the low-energy outcome of a more symmetric, unified framework that behaved differently when the universe was hotter? A simple analogy helps. Consider water freezing. The underlying molecular laws don't suddenly change at 0 degrees Celsius, yet the behavior shifts dramatically. Liquid becomes solid, symmetries break, and new large-scale properties appear. Something similar may apply to particle physics. The forces we observe today, electromagnetic, weak, and others could be distinct phases of a deeper, unified interaction that separated as the universe cooled and symmetries broke. This idea is attractive. But again, the key question is, what can we test? Physicists search for relics of early phase transitions, predicted particle relationships, cosmic defects, or measurable patterns in force strengths. Some predictions hold up, many don't, and that elimination process is valuable because it narrows the space of viable theories. The goal isn't to accumulate possibilities, but to discard incorrect ones. Yet even with symmetry breaking and unification models, the deeper issue remains. Why are there quantum fields at all? Why is there anything capable of fluctuating? Here, language often becomes sloppy. People say quantum mechanics allows particles to appear from nothing, but in quantum field theory, the vacuum is not nothing. It's a structured state governed by laws and fields capable of excitation. If you truly start with absolute nothing, no fields, no equations, no framework, then even the uncertainty principle has no meaning. Many creation from nothing ideas quietly assume mathematical structure from the start. So precision matters. And even if total energy could sum to 0, with positive matter energy balanced by negative gravitational energy, that's bookkeeping, not a mechanism. A balanced ledger doesn't explain the transaction itself. This takes us directly to the frontier of modern physics, quantum gravity. When we approach the earliest moments we can meaningfully describe, space-time curvature becomes extreme, and quantum effects can no longer be ignored. Our usual picture fields existing within space-time may break down entirely. It's possible that space-time itself is quantized or emerges from more fundamental ingredients. If that's true, then asking, "Where did the universe come from?" might resemble asking, "Where ocean waves come from?" while forgetting that the ocean itself has deeper structure. The beginning might not be a moment in time at all, but a boundary where our familiar idea of time stops applying, replaced by something more basic that only behaves like time under certain conditions. You might feel this is unsatisfying, that we started with a simple question and ended with words like emergent and boundary. But notice what's actually happened. We haven't abandoned explanation. We've mapped the territory where explanation is reliable and identified exactly what's still missing. The missing pieces aren't just more data, they're conceptual frameworks, a consistent quantum description of space-time, a clearer understanding of initial conditions, and predictions that can distinguish between competing ideas. There's one more clue that often goes unmentioned, yet it's deeply important: the arrow of time. The universe has direction. Eggs scramble but never unscramble. Heat flows from hot to cold. Entropy increases. That direction appears tied to the universe beginning in an extraordinarily low entropy state. Why should the early universe have been so ordered? If you want to understand where everything comes from, you can't ignore that the universe contains not just matter and laws, but a very specific history, one that allows complexity, structure, and eventually life to develop. So perhaps the deepest origin question connects here. Why did the universe begin in a state that allows time to have direction and structure to form? Answering that might not only explain where atoms come from, it might explain why coming from is a meaningful idea at all. And that leads to an even sharper question. What physical principle, testable, quantitative, and not merely verbal, could explain both the universe's low entropy beginning and the existence of the laws that allow an evolving cosmos in the first place?